Cosmic abysses. An introduction to black holes. Black holes. Just the name evokes a sense of mystery and awe. These enigmatic entities have fascinated scientists and stargazers alike for centuries. These cosmic entities are regions of space-time where gravity's pull is so strong that nothing, not even light, can escape. They are the ultimate gravitational traps. Imagine a place where the very fabric of our universe collapses in on itself, a place where the known laws of physics break down. That is the essence of a black hole. A region where the gravitational pull is so intense that it warps space and time. Black holes are not empty voids. They are incredibly dense objects with a gravitational pull that can capture anything that comes too close. They are formed from the remnants of massive stars that have reached the end of their life cycles. When these stars exhaust their nuclear fuel, they undergo a dramatic collapse. These stellar remnants are incredibly dense, packing an unimaginable amount of mass into an incredibly small space. This process creates a singularity, a point of infinite density. This extreme density creates the extraordinary gravitational pull that defines a black hole. Anything that crosses the event horizon, the boundary around a black hole, is lost forever. These objects are a profound testament to the power of nature and the mysteries that still linger in the cosmos. They challenge our understanding of physics and the universe. Let's journey together into the heart of these enigmatic objects, where the known universe confronts its most extreme limits. Join us as we explore the fascinating world of black holes and uncover the secrets they hold. Gravity's pull, a cosmic dance. To understand black holes, we need to grasp the concept of gravity. Gravity is the invisible force that governs the motion of celestial bodies, from the smallest particles to the largest galaxies. It is the glue that holds the universe together, dictating the orbits of planets, the formation of stars, and the structure of galaxies. Gravity is the force that attracts objects with mass towards each other. It was famously illustrated by Sir Isaac Newton when he observed an apple falling from a tree. This simple observation led to the groundbreaking realization that the same force pulling the apple to the ground also keeps the moon in orbit around the Earth. Imagine a bowling ball placed on a stretched rubber sheet. This analogy helps us visualize how gravity works in the fabric of spacetime. The bowling ball represents a massive object like a planet or a star. The bowling ball creates a dip in the sheet, much like how massive objects create a dent in spacetime. This dent is what we perceive as gravity. The more massive the object, the deeper the dent, and the stronger the gravitational pull. This dent is what we perceive as gravity. It is a curvature in the fabric of space-time caused by the presence of mass. The greater the mass, the more pronounced the curvature. Now, imagine that bowling ball being replaced with something much denser, something like a small marble with the same mass. This marble, despite its smaller size, would create a much deeper, more pronounced dip in the rubber sheet. The marble would create a much deeper, more pronounced dip in the rubber sheet. This is because the same mass is now concentrated in a smaller volume, increasing the density and thus the gravitational pull. This is similar to how black holes warp space-time. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape their pull. They are formed when massive stars collapse under their own gravity, compressing their mass into an incredibly small volume. The more massive an object, the stronger its gravitational pull. In the case of black holes, their immense mass and density creates such a profound curvature in spacetime that they become points of no return, known as event horizons. Black holes take this to the extreme, warping spacetime to such an extent that nothing can escape their grasp. They are the ultimate expression of gravity's power, a cosmic dance of matter and energy that continues to captivate and mystify scientists and astronomers alike. The point of no return, the event horizon. Surrounding every black hole is an invisible boundary known as the event horizon. This is the point of no return, a threshold beyond which the gravitational pull is too strong to overcome. Think of a waterfall. As water approaches the edge, it flows faster and faster. Beyond the edge, there's no coming back. The event horizon is like the edge of that waterfall. Once something crosses it, it's destined to fall into the singularity at the black hole's center. Even light, the fastest thing in the universe, cannot escape the pull once it crosses this boundary. Stretching the limits spaghettification. What would happen if you got too close to a black hole? This question has fascinated scientists and space enthusiasts alike for decades. Black holes, with their immense gravitational pull, are some of the most mysterious and powerful objects in the universe. You wouldn't simply be crushed, you would be stretched, like spaghetti. This bizarre and somewhat terrifying process is known as spaghettification. This phenomenon, aptly named spaghettification, is a result of the extreme tidal forces near a black hole. These forces are so powerful that they can distort and stretch anything that comes too close. Imagine your feet are closer to the black hole than your head. The gravitational pull would be much stronger on your feet than on your head, creating a significant difference in force. This difference in gravitational pull, known as a tidal force, would stretch your body, pulling it apart like taffy. The closer you get to the black hole, the more extreme this stretching becomes. This difference in gravity would stretch your body, pulling it apart like taffy. The process is gradual but relentless, and there's no escape once you're caught in the black hole's grip. As you fell further in, the difference in gravitational pull between your head and your toes would become more and more extreme, eventually stretching you into a long, thin stream of atoms. This is the ultimate fate of anything that ventures too close to a black hole. This is just one of the strange and fascinating ways that black holes can distort the fabric of space-time. They are not just cosmic vacuum cleaners. They are complex and enigmatic objects that challenge our understanding of physics and the universe. Section 5. Time warps. Gravity's effect on time. One of the most mind-bending concepts in astrophysics is that gravity affects not only space, but also time. This phenomenon is called gravitational time dilation. Imagine you're walking through molasses. The thicker the molasses, the slower you move. Similarly, the stronger the gravitational pull, the slower time passes. Near a black hole, where gravity is extremely strong, time slows down significantly relative to an observer farther away. This means that if you were to observe someone falling into a black hole, you would see their clocks slowing down as they approach the event horizon. From their perspective, time would seem to flow normally. However, from your perspective, they would appear to freeze in time, forever frozen at the edge of the abyss. Section 6. Light's distorted journey. Gravitational lensing. Black holes don't just affect time, they also distort the path of light that passes nearby. This phenomenon, known as gravitational lensing, is another testament to their immense gravitational pull. Imagine a glass of water placed on a table. If you look through the glass at an object behind it, the object appears distorted. This is because the water bends the light passing through it. Black holes do the same thing, but on a much larger scale. Their gravity bends the path of light rays that pass close by, distorting and magnifying the images of objects behind them. This lensing effect allows astronomers to study objects that would otherwise be too faint to see. It's like having a giant magnifying glass in space. Section 7. Unraveling the mysteries black hole research. Black holes remain one of the most intriguing and challenging areas of research in astrophysics. Scientists are constantly working to understand how these objects form, how they evolve, and how they interact with their surroundings. Telescopes around the world and in space are constantly observing black holes, collecting data that helps us piece together their mysteries. We are living in an exciting time for black hole research. With new technologies and collaborations, we are on the verge of unlocking some of the universe's most closely guarded secrets. Section 8. Black holes and the fate of the universe. Black holes also play a crucial role in the grander scheme of the universe. They influence the formation of galaxies, the distribution of matter, and even the ultimate fate of the cosmos. Some scientists believe that supermassive black holes, millions or even billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. These cosmic giants are thought to have played a crucial role in the formation and evolution of galaxies. Understanding black holes is therefore not just about unraveling the mysteries of these extreme objects, but about understanding the universe as a whole. Their existence challenges our understanding of physics and pushes the boundaries of human knowledge. Section 9. Conclusion: the allure of the unknown. Black holes represent the ultimate cosmic frontier, places where our current understanding of physics breaks down. They are a testament to the power of nature and the vastness of the cosmos. While we have learned much about black holes, they continue to hold many mysteries. As we continue to explore the universe, we will undoubtedly make new and even more astonishing discoveries about these enigmatic objects. The quest to understand black holes is a journey into the heart of the unknown, a journey that promises to challenge our assumptions and expand our horizons. And it is a journey that is just beginning.